Welcome! Today, we're going to break down an incredibly cool and really powerful algorithm for finding the shortest path between 2 points. It's called breadth-first search, and to get our heads around it, we're going to start with a simple, everyday kind of puzzle.
So, picture this. You're in San Francisco, you're at Twin Peaks, and you want to get to the Golden Gate Bridge. The catch, you're taking the bus and you absolutely want to make the fewest transfers possible. You've got the whole bus map in front of you, so where do you even start?
Well, the most logical place to begin is to check all the spots you can get to with just one bus ride, right? So we look at all the direct routes from Twin Peaks and, nope, the Golden Gate Bridge is not on that list. Okay, so a one-and-done trip is out.
All right, Plan B. Let's widen our search. We'll now look at every single stop we could reach in one transfer, and then check all the places we can get to from all of those stops. We're now looking at every possible two-transfer destination. We scan that list, and still no Golden Gate Bridge. Okay, we're getting further out, but we're not there yet. So we expand one more time. We take all those two-step places and find every single place they connect to. And this time, bingo, there it is. The Golden Gate Bridge finally pops up. We found a way. And here's the cool part. Because we checked all the one-step routes, then all the two-step routes, and only then the three-step routes, we know for a fact this is the shortest path.
That little bus puzzle we just solved is a perfect example of what's called a shortest path problem. It's all about finding the minimum something, in our case bus transfers, between a starting point and an ending point. And that methodical, layer-by-layer way we did it, that is the absolute heart of the breadth-first search algorithm.
To really tackle this kind of problem and any problem like it, we need a solid two-step plan. First, we have to take our bus map, our problem, and represent it in a way a computer can understand. We need to model it as a graph. And then, once we've got that model, we can unleash the algorithm on it to find the answer.
So let's talk about step 1, modeling with graphs. Now, when you hear the word graph, you're probably thinking of those X and Y axis charts from math class. Forget those. In this world, a graph is something way, way simpler. It's just a map of connections.
Yep, that's all a graph is. It's a way to show how things are related to each other. And it's only made of two things, nodes and edges. Seriously, just think of it as dots and the lines that connect the dots. That's the whole idea.
So the nodes, those are the dots, are the individual things themselves. They're the bus stops or maybe people in your friend group. The edges, the lines, are the connections between them. That's the bus route that joins two stops or the friendship that connects two people.
Let's make this super concrete. Imagine a poker game. Alex owes Rama some money. Okay, we can draw that. We make a node for Alex, a node for Rama, and an edge, an arrow, pointing from Alex to Rama. Done. Now what if Tom owes Audit? We just add two more nodes and a new edge. And if Rama also owes Audit, we don't need new nodes, we just add another edge from Rama to Audit. All of a sudden, this messy list of who owes who becomes a really clear visual map.
Okay, so we know how to turn our problem into a graph. Now for step 2, actually solving it. This is where we bring in the master key, the special tool designed to work on these graphs. Breadth-first search, or, BFS for short.
And what makes BFS so useful is that it's a multi-tool. It can answer two really big questions for us. First, it can just tell you, hey, is there even a path from point A to point B? But more importantly, it doesn't just find a path. It finds the absolute shortest one.
Now, to see how BFS actually pulls this off, let's switch gears. We're going to use a new analogy, something a little more personal. This is going to let us see the step-by-step logic in a way that just clicks.
So, here's the new scenario. You're looking for someone who sells mangoes. I know, a little random, but stick with me. You want to find a seller who's in your social network, but obviously you'd rather find a direct friend who sells them, not a friend of a friend of a friend. So how do you search for them in the most efficient way? This is the BFS strategy in a nutshell. First, you make a list of all your direct friends, your first-degree connections. Then, you start checking them, one by one. You check your friend Alice. Does she sell mangoes? No? Okay. Now here's the crucial part. You take all of Alice's friends and add them to the very end of your search list. Then, you move on to the next person on your original list, and you just keep repeating that process. You see what's happening here? This whole process forces your search to move outwards from you, like ripples in a pond, one layer at a time. You are guaranteed to check every single one of your direct friends before you ever even start looking at any of their friends who are your second-degree connections. And that right there is the beautiful, simple genius of it. Because of this strict layer-by-layer search order, The very first mango seller you find is guaranteed to be the one closest to you. The algorithm structure just naturally leads to the shortest path. It can't happen any other way.
But what's the secret? What's the mechanism that keeps everything in this perfect, tidy order? How does the algorithm make sure the first people you add to the list are the first ones you check? The answer is a specific kind of data structure. It's the secret weapon behind BFS.
It's called a queue. And honestly, you already know exactly how this works. It's a line, just like waiting for a bus. The first person to get in line is the first person to get on the bus. It's that simple. First in, first out.
And this is the big aha moment. Using a queue, first in, first out, is absolutely critical. Our search list has to be a queue, because if we used a different tool, like a stack, which is last in, first out, or LIFO, the whole thing would fall apart. We'd end up immediately searching the friends of the very last person we added. We'd be diving deep down one random branch of the network instead of searching layer by layer, and we'd completely fail to find the shortest path.
So that's the takeaway. The simple, fair, first-come, first-served logic of the queue is the #1 thing that makes breadth first search work. It's the engine that powers the whole thing and guarantees that we get the right answer.
And this isn't just for fun puzzles about buses or mangoes. This idea of finding the shortest path is absolutely everywhere. BFS is a fundamental algorithm running behind the scenes in spell checkers, trying to find the correct word with the fewest edits. It's used in networks like LinkedIn to find a doctor in your area, and it's even used by search engines to crawl and map the entire internet.
So, there you have it, from a simple puzzle to a tool that powers some of the most complex systems we use every day. That's breadth first search. It's just a beautiful example of how thinking about a problem in the right way and using a simple, methodical search can solve huge challenges. And that leaves me with one final thought for you. Now that you see this pattern, what's the shortest path to something you want to achieve?